Another illustration of Pascal's principle is that of a balloon filled with a gas attached also to some form of piston. So imagine a balloon that expands elastically, automatically, such that P is constant and the pressure is P1 everywhere. And now you take a piston and you apply a force to compress the air in the balloon, and as a result the balloon will expand, and the force of the compression is distributed uniformly such that now the pressure is some higher pressure P2 everywhere. So it's not the case that, for example, the area near the point of where the force is applied is larger than somewhere else in the balloon, but rather pressure is distributed uniformly and is the same everywhere in your balloon. Now let's consider what this means for the pressure of a fluid where gravity does act. So let's consider pressure at a depth in a fluid. So for example, you have some container with a cross-section A, and it is partially filled with some fluid. The rest is vacuum, and gravity is acting downward. And let's consider some given depth here that is at a distance h from the surface of the liquid, and we'll consider two forces, namely force acting down from the overburden of the water, and then a response force that acts upward. So the downward force, Fd, is just the mass of the liquid above that height times acceleration due to gravity, g. So Fd is density of the liquid times the height h times the cross-sectional area A times g. And since nothing is moving or accelerating, the force down and the force up have to be balanced. They have to be the same. So the upward force is also rho L H A G, and the corresponding pressures are just the force divided by the area. So we have PD is rho L H G, and PU is rho L H G. So imagine you're, for example, 10 meters underwater, and then your pressure that you experience is rho L, which is about 1,000 kilogram per meter cubed, times 10 meters, times roughly 10 meters per second squared. Really, G is not 9.81, but if we just do one significant figure, then we find here that this is about 10 to the 5 kilogram meters per second squared, which is 10 to the 5 Newton per meter squared, or 100 kilopascal. And 100 kilopascal is roughly 1 atmosphere. For pressure, we have a whole lot of confusing units. We have atmospheres or bar or Pascal, and I'll get back to that in a little bit. 1 atmosphere is the unit defined at the surface of the Earth due to the pressure of the column of air above us. So that is the pressure that we experience if we live at sea level roughly, and that is 103 kilopascal. So that means if you go down 10 meters under the surface of the ocean, you are doubling the pressure that you've experienced. You get the 1 atmosphere from the air, and then another atmosphere from the pressure of 10 meters of water above you. So in the real world, P at 10 meters below zero is approximately 2 atmosphere. And I should say, since we're considering the pressure at the same height here, we don't really need to define pressure down and pressure up, right? Because pressure has no direction, as we learned in the previous lecture. Now, Finally, we'll consider the mercury barometer, which works as follows. Consider a bath of mercury, Hg, and then a test tube also filled with Hg. And you turn this test tube upside down and you place it in your mercury bath. In this case, the overburden of the mercury in the test tube will displace some of the mercury in your bath, and that depends on the pressure, on the ambient pressure that acts on your mercury bath. So that's approximately 1 atmosphere pressing down here. And so at this level here, you also have a pressure P0, which is 1 atmosphere, right? Since pressure is the same at the same height everywhere. And you're left with a vacuum here and a certain distance h. Now, what is the distance h? Well, the pressure at P0 is the same as the pressure due to the overburden, which is the density of mercury times G times H. And so we can solve this for H, which is the only quantity we don't know. So we have P0 over rho Hg times G, and rho Hg is about 13.6 times the density of water, so it's rather heavy, 13.6 times 10 to the 3 kilogram per meter cubed. And so I can plug these numbers in here. We have P0 we know is 1 atmosphere, so it's 103 times 10 to the 3 Pascal, divided by 13.6 times 10 to the 3 kilogram per meter cubed, times 1 over 9.8 meters per second squared, which gives you about 77 centimeters. And I urge you, as an exercise at home, to make sure that you understand that these units simplify to meter. And so if the atmospheric pressure drops, your H will decrease, and you can calculate the pressure drop by your difference in H. And this concept is used in weather predictions when you know whether a low pressure system might be moving in or a high pressure system.